All right, ladies and gentlemen, recording started. So, on Friday, we introduced the concept of force. Force, we said, fits along into that mechanics idea, the study of motion. It's the next big part. When we started studying mechanics, there were 4 questions that we wanted to answer about the motion of an object. What were those 4 questions that we wanted to know about the motion of an object? We started studying mechanics. Where is it? What is it doing? What's it going to do next? When does all this happen? All right? So on Friday, introducing force, we added in another question. Do you remember the other question that we added in? I think I mentioned it in passing, but not necessarily officially. Well, what do forces do? What's our definition of force? We can go back to your outline from the other day. So, what do forces do? Zin? Push and pull an object. That's what they are. More importantly than that, though, what do they do? Forces cause, kind of good. Acceleration. Forces cause things to change what they are doing. So now we add in a 5th question, and that question is why? Why do all these things happen? And the answer to that question is because of force. Okay? All right, so forces cause acceleration. What did we talk about? 2 kinds of forces, or 2 sort of ways that forces can work. What are the 2 ways that forces can cause other objects to accelerate? Bad question. All right, Andy, go ahead.
Electromagnetic forces.
Yeah, that's not the question I wanted. So, contact force versus field force. Andy, what's the difference between a contact force and a field force?
Contact force is when 2 things touch.
Contact force, relies on contact, but a field force can do what?
It can push or pull an object from around it.
Even though they aren't,
making contact.
even though they aren't actually in contact, right? So you got gravity, we got electromagnetic forces, and then magnetic forces, stuff like that, right? All right, and then on Friday, we talked about, or we finished talking about the different types of forces. So we talked about electromagnetic forces, right? Electromagnetic forces are basically what? Summarize electromagnetic forces for me.
Forces between charged particles.
Those charged particles, Connor, we learned earlier in the year are what? Protons and electrons, right? Just depending on their numbers, that can be a big force or a small force, right? So electromagnetic forces are protons and electrons, right? And then we talked about weak nuclear force, strong nuclear force that act on the atom itself to kind of hold it together. And then at the very end, we didn't get to this one, so we'll pick it up from there, right? So the 4th type of force that exists out there is gravity. And gravity is kind of a mysterious one. So first, you guys know a little bit about gravity, right? What does gravity do to things? Mark, go ahead. Here on Earth, yes. But more generally, what does gravity do to things?
Pulls things.
Pulls things
towards it.
Towards or together, right? Mark, now that number comes in here in a second, right? But here on Earth, we know that gravity causes that acceleration, but at different places in the universe, that value can change, right? So, gravity is an attractive force between any 2 masses that are in the universe. Gravity is a much weaker force if you look at it in comparison to, say, electromagnetic force or something like that, right? Evidence that gravity is a comparatively weak force, right? So if you're at a birthday party, okay, and you take a balloon, and if you have hair, you rub it against your hair, right? Okay, and then you can stick it to the ceiling. Yes? We've seen this done before, right? So, you've taken, and we talked about during the electricity unit that electrons get stripped away from one object and onto the other object, and now there's an imbalance, so that object is charged, and it attracts to the other things that are in the ceiling, right? But that one balloon with, its imbalance of protons and electrons holding it to the ceiling is stronger than the entire gravity of the whole Earth pulling it down, right? Because if it wasn't, it would fall. But just that imbalance of protons and electrons on the balloon is enough to counteract the force of gravity from the whole Earth pulling on it. So gravity is a relatively weak force. But we don't think of it that way because it's the one that we kind of are most familiar with. The one thing that really influences it, right, it acts over a very long distance. So even though gravity is comparatively weak when we compare it to the other forces, it does act over very long distances, like our solar system, or the galaxy, or the universe itself. And we kind of talked about that, how it might affect how the universe ends and stuff like that. All right. Greater the mass of the objects, the greater the gravitational force between them. So there's a direct relationship there. More mass, more gravitational force, right? So Mark, going back to like that number, right? That's the number that you're about 10 based on here on Earth, right? The amount of mass the Earth has and how much gravity it has, right? That's what number we end up with. But if we go to some other place that has more or less mass, that number can change, right? But the other thing that affects the amount of gravity is distance. And as distance between two objects increases, gravitational force decreases. So we have an inverse relationship there. And the balance between how much mass something has and how far away we are from it ultimately gives us to, okay, what is the gravitational acceleration at that point, around that object. All right, good there? Okay. So let's take and go ahead and put that away. Oh, sorry, one thing. We talk about the inverse square relationship. Sorry, I should introduce you to this. Yes, it is true that as you get farther away from an object, the amount of gravitational force that you feel decreases, but it is not a direct relationship. It's what we call an inverse square relationship. So notice, you have F, and then squiggly equals sign, right? Because it's not exactly equal. There's some other factors that go into it, but it's related to it, okay? But it's 1 over d squared, where d represents the distance. So if if you're a certain distance away from the Earth and you feel a certain acceleration from gravity, right? So here, like Mark, on the surface, right, the acceleration we feel from gravity is about 10 meters per second, right? If we went twice as far away, now, here's the kind of kicker thing, right? You have to go twice as far away from the center of the Earth. So, like if you're on a ladder that's 10 feet above the ground, and then you climb a different ladder, and now you're 20 feet off the ground, you're not twice as far away from the Earth, right? Because you got to factor in the radius of the Earth and all that, okay? But if we went to a distance, picture. So, here, okay. There's Earth. There's you, okay? Right now, as you stand on the surface of the Earth, you are actually this far away from the middle, okay? And as a result, the acceleration here is 10 meters per second squared, okay? But let's say you went this far away from the middle, okay? Now you're twice as far away. Good? Yes? Going back to this relationship, nope, not that one, this one, F is approximately equal to 1 over d squared, okay? First, the d is in the bottom of this fraction, right? So as d gets bigger, what happens to F? Smaller. That's the inverse relationship, right? So as you get farther away, as the distance increases, the force of gravity that you feel decreases. But by going twice as far away, so let's say this is distance equal to 1, right? It's not 1, but it's not 1 anything. Let's just say it's 1, right? When you go here, right, now your distance is what? 2. Right? When we plug that in, we end up with what fraction now? 0.25, or 1/4 as much, right? So, if the acceleration on the surface, is 10 meters per second squared, when you get up here, what's the acceleration going to be now?
2.5.
2.5. Because Andy, what is 2.5 compared to 10?
1/4.
It's 1/4, right? So even though we only went, oh my goodness, 2.5. So even though we only went twice as far, we're experiencing 1/4 as much gravity. Andy, go ahead.
Does that mean that in the center of the Earth, the force of gravity is 40 meters per second?
No, because gravity depends on mass, right? So right now, when you're in this spot, all of the mass of the Earth is pulling you in the same direction, right? It's all pulling you back toward down, because it's all on the left-hand side of you as it sits on the board, right? But if you go here,
It's all pulling from different directions.
it's all pulling in different directions. So how much gravitational force would you feel at that point?
0.
0. Okay? And that'll be an important thing we get into a little bit more. We said that's a certain thing. Yeah, so what would it be like? It'd be like you were in space. Not because there's no gravity in space. Okay? But that's kind of, but it would be like you'd be like you could float, you could do this and that and the other thing, right? It wouldn't be like you were standing on the ground because all of that gravity is pulling you in different directions. Okay? Kind of good.
If you were in the center of the Earth, does that mean that you would only be in one spot?
Technically, yes. Although that one spot is a little hard to quantify because the Earth isn't a nice perfect sphere. You know what I'm saying? Like there's certain parts that have more mass than other parts. So it's kind of hard to say this is the middle, right? Where the middle is a little bit tricky. But if you could find that middle spot, you would have a gravitational acceleration then of 0. All right, good there? Okay. Let's move on to here. And this is the new outline that I gave you today. All right. Okay. So, up on the board, there's a picture of Newton. He's kind of important to this chapter. Okay. This is the young Newton, his flowing, luxurious hair. Yeah, you may know the old Newton with his white powdered wig. He's much more dashing in this picture, don't you think? So, Jordan thinks so. All right, but in his hand is a book that he wrote back in the 1680s. So here's the story of Newton, quickly, in a nutshell. There's way more to it than this, but. So Newton grows up in the middle 1600s, 1640, I want to say 2, but I'm not 100% sure on that. So anyway, so Newton's born in England, 1640s, and goes to college when he's about 17, and he's there for a little while, and then he gets sent home back to his family's farm. Not because he was bad or got in trouble or whatever, but the plague was rolling through England, doing its thing of killing people. So large conglomerations of people, large congregations of people aren't good. That's really good for the transmission of the plague. So places like universities and things like that, they sent everybody home because they didn't want them to get the plague and die. So Newton goes back to his farm, and farming, really not his thing, so he just kind of sat around the farm and, watched everybody else work, I guess, I'm not really sure. But starts sort of making observations about the world and how things work and, kind of writing some things down and stuff like that. And then allegedly, I don't know if it happened because I wasn't there, but allegedly an apple falls from the tree and hits him on the head. I don't know, maybe it happened, maybe it didn't, who knows. Okay. But regardless, he starts making some observations about the world, how it works, what he thinks is happening in this situation and that situation. So then, goes back to college, becomes a professor. About 20 years later, he's talking to other professor-y type people, and one of his friends, Edmund Halley, if you ever heard of the comet, Halley's Comet, right? Apparently him and Newton were bros, and you know, he kind of came across, Halley was sort of looking at Newton's stuff and kind of came across these things that he was doing while he was on his farm, and said, hey, what's going on here? It's like, I don't know, some things I was, you know, looking at, things I was measuring, making some observations. And Haley goes, yeah, this is pretty good. You should probably write these things down, maybe publish a book, you know, because it's pretty good stuff. And so he writes this book. It's called The Principia, and published, I think, in 1687, if I remember correctly. Not that you need to know that, but and it ends up being like the laws that fundamentally, you know, govern the universe, motion in the universe, right? Just some things that he was messing around with, watching an apple fall from the tree, you know. You know, there were a couple things that he couldn't quite figure out mathematically, and so he invented math to kind of make everything work out, and today we call that math calculus. So, you know, he might have invented calculus in his spare time, just, you know, because he couldn't figure something out, so he just, you know, like, hey, I'll invent math to make it work, and there you go. So that's the kind of guy Newton was. So anyway, Newton's first law, Newton's second law, Newton's third law. 3 laws that, like I said, govern motion in the universe. So we're going to start with Newton's first law and Newton's second law, because they're much more closely related than Newton's third law. So let's start with Newton's first law. I will not make you recite it, you know, by memory, but most of you probably at least have heard it before. So Newton's first law states, an object at rest remains at rest. An object in motion continues in motion with a constant velocity until it experiences a net external force. An object at rest remains at rest. An object in motion continues in motion with a constant velocity until it experiences a net external force. All right. So, Newton's first law has 2 parts. The first part is pretty good. An object at rest remains at rest. No problem, right? Everybody's pretty much in agreement with that. The second part is the one that takes a little convincing. An object in motion continues in motion with a constant velocity. That was kind of hard for a lot of people to accept at the time, because in the whole of human existence, if something was moving, what did it eventually do? Stops, right? Everything you've ever seen in your life that was at one time moving eventually stops. So, before Newton came along, that was the prevailing thought of the time, that there must be something special about being at rest, that was the quote-unquote preferred state of an object. Look, there it is. Why would it ever move from rest? It's so happy, content, right? It only moves because you make it move, right? But what Newton says is, no, not really it. While yes, an object at rest will remain at rest, but an object in motion will actually keep going. It's you or something else that makes it stop. If that something else wasn't there, it wouldn't stop on its own. It would just keep going and going and going and going and going with a constant velocity. In order for something to have a constant velocity, what has to be true? 2 things.
No gravity and no distance.
Same.
Think about our definition of velocity.
Same distance and same displacement.
Same speed, same direction. So something that's moving wants to continue moving in a straight line at the same speed. It will only change from that path if something makes it change from that path. And Newton calls that idea inertia. Okay? So inertia basically sums up Newton's first law. All right, inertia. It is an object's nature to resist changes in motion. An object resists changes in motion. It's not in an object's nature to stop once it is set in motion, which was, like I said, the prevailing feeling of the time that kind of came about along in the time, the ancient Greeks. A lot of our original ideas come from Aristotle, right? If we think about it, something stops. It always stops. So there must be something special about being stopped, right? We call this idea inertia. Okay? The tendency of an object to maintain its current state of motion is known as inertia. So a couple of practical examples of inertia. We'll start off with serious, and then we'll move to more funny. Okay? All right. So this one's about as serious as you get. Not that you might ever find yourself in this situation, but if we think about it, from a practical standpoint. Okay. So you ever watch nature videos or something on Discovery Channel or whatever? Not like Wicked Tuna or whatever shows. Like when sometimes they actually show like educational shows on the Discovery Channel. But like if you've ever watched animals on the African savannah, okay? Lion goes to hunt the gazelle or whatever it's hunting, okay? And so it starts chasing the gazelle. How does the gazelle run? Anybody? It does kind of jump, but it does something else a lot. It changes direction, right? It changes direction. Why? Because it's harder for the lion to continue chasing it if it keeps changing directions, right? Because the lion wants to keep going straight, okay? And you might say, well, isn't it harder for the gazelle to change direction? Yeah, it is. But there's a reason why it's easier for the gazelle to change direction than it is for the lion to change directions. Okay, we'll talk about it in a second. Okay? Second, maybe a little more practical example for you guys, right? So if you've ever done any conditioning for sports in any way, shape, or form, I think most of us have probably done something like that, okay? So you got options. You could run a mile, just run it straight, right? Start, stop, run 4 laps of the track, right, continuously. Or you can start, run 20 yards, stop, turn around, run 20 yards back, stop, turn around, run 20 yards back, stop, turn around, and just keep doing that back and forth, back and forth, back and forth, right? Which one's preferable? 4 laps is a lot easier than stopping and turning around and stopping, turning around and starting back up again every time. Why? Every time you slow down, stop, and turn around and go back the other direction, right? You're fighting your body's inertia, right? It's harder for you to stop, slow down, stop, change directions, start back up the other way. Why? Because your body doesn't want to stop. It wants to keep going, right? So that's why those things are a little bit harder to do, okay? Last example. Maybe not, as practical, but definitely funny, but, it has good application. So let's say June 17th, so 3 weeks from today, okay? Your first day of summer, right? I'll still be here because I'll be working, right? I have to work one more day than you guys do. So I'll still be here, right? But you guys will be, at home, okay? And, it's your first day of summer, right? Maybe you want to, take it easy a little bit, right? So you decide to sleep in. And you end up staying in bed till, I don't know, noon, right? Noon 30, right? It's been a rough year, right? Okay. So your mom, understandably, right, might get a little upset. Okay? So she comes, she yells at you. Get up, it's noon 30, right? So, what's your response? You have a built-in response now. Mom, it's not my fault, right? It's Newton's fault, right? Newton Newton says it's in my nature to resist changes in motion. An object at rest wants to stay at rest, right? For me to walk down the steps and like get my day, that's unnatural. I'm fighting the laws of nature, all right? So, see what you can do, right? You might get smacked, I don't know. Just give it a go, see what happens. Like, but Mom, I learned so much this year. All right, so inertia. It's not in an object nature to change. It's in an object, or stop. It's in an object's nature to continue doing what it's doing. Whether that's stopped, laying in bed, or whether that's already moving, like when you run, back and forth, okay? So, what tells us about inertia? An important factor that we have to consider here is an object's mass. We've talked about mass a lot of times throughout the year, right? Mass is a measure of the amount of matter that comprises an object, and that's true. But the other thing that mass does for us is that it lets us know how much inertia an object has. Mass is a measure of an object's inertia, how much it wants to continue doing what it is already doing. So, a couple practical examples, right? So, Andy, just because you gave me that face when we were talking about before, right? If we go back to our example of the lion and the gazelle, right? The gazelle changes directions because it's harder for the lion to follow it if it keeps changing directions, right? But isn't it hard for the gazelle to change directions? Well, yeah, harder than running straight, but if you look at the size of a gazelle versus the size of a lion, right? Which one's bigger?
The lion.
The lion, right? More mass, harder for that lion to change directions. The more mass means the lion has more inertia. So that lion wants to keep going straight. Okay? Some other practical examples that you may have seen before. If you're sitting in a car, and you guys are getting close to driving now and stuff like that, but if you're sitting in a car, right, you're at a stoplight, and there's a truck next to you, right, a big dump truck or a semi-truck or something like that, right? The light turns green, both vehicles hit the gas. Which one's going to go faster? Which one takes off from the stoplight faster? Car takes off from the stoplight faster. Why? Well, how big's the car compared to the truck? It's a lot smaller, right? Meaning that it has less inertia. It's easier for it to start moving, right? That truck with its big mass has a lot of inertia. It wants to continue at rest. But it also works the other way too. If the car and the truck are on the highway and they're both traveling 65 miles per hour and they both slam on their brakes, which one's going to stop first? The car stops first because it's easier for the car to stop than it is for the truck to stop. Why? It has more mass. Or the car has less mass, the truck has more mass. The more mass something has, the harder it is to change what it's doing. That might be starting, but it might be stopping. It also might be what? Changing direction, right? The more mass something has, the harder it is to change its motion. All right, good there? So Newton's first law deals with things staying the same. Newton's first law deals with things staying the same, which means Newton's second law should probably deal with what? Changing, right? Newton's first law says things don't change unless you make them change. Newton's second law then gets into, okay, well, if we make them change, how much do they change? So a couple of things we have to get into before we get to Newton's second law. First, the idea of net force. You will see net force symbolized by two things. Sometimes you'll see it as F with just a little subnet next to it. But a lot of times you'll see it with this Greek letter in front of it. This is a Greek letter sigma, okay? Looks like a sideways M, right? The sigma represents the sum or the total of something. You will come across this in math class. I think it's in Algebra 2 when you talk about like sequences and series and things like that, okay? but it's a mathematical symbol that represents the sum or the total of something. In this case, if we put it in front of F, that means it's the total force, or the sum of the forces. So the net force is the combined effect of more than one force that is acting on an object. The combined effect of more than one force acting on an object. Or, mathematically, the sum of all the forces acting on an object. Very rarely will we encounter a situation where there is only one force acting on an object. Right? Here's the ball. If I let it go, what happens? It falls because of what? Gravity. But does that mean gravity only acts on it when I let it go? Gravity's always acting on it. But here, it's not falling, but here it is. Why? Because what? Because of my hand, right? In this situation, now that ball has two forces acting on it, right? Gravity pulling down, but my hand pushing up on it. So like I said, very rarely will we encounter a situation where there is only one force acting on the object. So if we want to look at what's going to happen to an object, we have to look at the combination of all the forces, right? Here, which one's stronger, gravity or my hand?
Neither.
If my hand was stronger than gravity, what would it do? Right? So here, what would we say about these forces? They are equal. They are the same. Okay? But the one thing that's different about them is what? Going different directions, right? Suzanne, how do we distinguish one direction from the other direction? No. How do we tell the up forces from the down forces? We call one what? We call the other one what? We call one positive and one negative, right? We probably, in this case, would call gravity negative because it's down, and we call my hand positive because it's up, right? Suzanne, if we add a positive force together with a negative force, what do we end up with? Could end up with 0, right? But we end up with something smaller than either one of them to begin with, right? So that's the idea behind the net force, okay? The motion of an object will only change if the net force is not 0. Here, as I hold this ball, right, my hand pushing up on it just as much as gravity is pulling down on it. The net force is 0. The combined effect of my hand and gravity is nothing. And therefore, nothing happens. Nothing changes, right? Inertia, right? It will stay this way unless something makes it change, okay? The motion of an object will only change if the net force is not 0. And that leads us to our next concept that we call, calculate net force. We just kind of talked about this, okay? Right? When forces are acting on an object are unbalanced, the object will accelerate. It will change what it's doing. We briefly introduced this, okay? Forces in the same direction are added. Forces in the opposite direction are subtracted. Because forces in the same direction, we have the same sign, right? But forces in the opposite direction would have different signs. If, right, tug of war, two forces, right? Now they're not up and down, but now they're left and right, so we would call one what and one what? How would we distinguish the blue from the yellow? One call one positive and call one negative, right? As long as it's one dimension, right? Before we were talking about the ball, it was up and down. Here it's side to side. It's still the same idea, right? So in this case here, right, when the forces acting on an object are balanced, when they have the same magnitude, but in the opposite directions, the net force is 0 and there's no change. Right? I'll give you that next part in a second. When this is the case, we refer to that object as being in equilibrium. When the net force is 0, an object is in equilibrium. Okay? What you wrote, what that says are the same thing, right? You know, it's just that's a little overused. But Jane, those two, that's what you wrote is basically an explanation of that, right? When the net force on an object is 0, we say that object is in equilibrium. If the net force is 0, what is that object going to do or not do? Change. Or if we use a term that we introduced last unit, it's not going to accelerate, right? When the net force on an object is 0, that means the acceleration of that object is 0. There are two physical examples of an object that has a 0 acceleration. An object that has 0 acceleration can look like what? What are two examples of an object that could have 0 acceleration? Harris, what's one? No motion. Okay? This ball has 0 acceleration, right? Okay. It's not changing what it's doing. That's one example. What's another example of 0 acceleration? Constant velocity, right? An object will remain at rest or it will remain in motion with a constant velocity, right? And Lorna, we said for something to have a constant velocity, what has to be the case? Same speed, same direction. So an object moving in a straight line at a constant speed is also in equilibrium. But again, that gets us basically back into Newton's first law. Inertia takes over, right? Whatever it was doing, it will continue doing. So, what if those forces aren't balanced? What happens? That's where Newton's second law comes in. So we said Newton's first law deals with things not changing, things in equilibrium, or the concept of inertia taking over. Newton's second law deals with things that have non-balanced forces. So, the acceleration of an object is affected by two things. The net force that's acting on the object and the mass of the object. So the acceleration of an object is affected by two things. Net force and mass. How is mass going to affect acceleration?
Inertia.
Yes. Will it have a direct effect or an inverse effect on acceleration?
Inverse.
Inverse, right? The more mass something has, the less it wants to change, right? So acceleration inversely affects, mass inversely affects the acceleration. What about force? How is force going to affect acceleration? Direct, right? Harris, if we hit a tennis ball, right? If you want to make it go faster, how hard should you hit it? Harder, right? Less force, less acceleration, more force, more acceleration, right? So that's what kind of relationship? Direct, okay? We summarize those two relationships with a real neat equation. That neat equation is F net is equal to m times a, or a is equal to F net divided by m. Those are the same equation, just rearranged algebraically. So F is equal to m times a, or a is equal to F over m. And that summarizes those two relationships that we just talked about. Acceleration is directly related to net force. Net force increases, acceleration increases. Net force decreases, acceleration decreases. And acceleration is inversely related to mass. If the mass goes up, acceleration goes down. As the mass goes down, acceleration goes up. All right, good there? that's pretty much going to take us through the next week. After that, it's all just kind of applying those two concepts that we introduced today, Newton's first law, inertia, Newton's second law, force, mass, and acceleration. I will update the calendar and include reading assignments and a couple of homework assignments off of those things out of your book. And tomorrow we start getting into applications. Okay?